Okay. All right, let's go on to some new stuff. So this next stuff, we're finishing up chapter 7. And what it is on modeling data using a couple of different types of functions that we haven't, well, we've actually talked about a couple of them, but we haven't talked about a couple other ones that we'll have to learn about. The first function we're going to, well, the ones we're going to talk about are called exponential, logarithmic, and quadratic. We've already seen quadratic ones. There's going to be exponential, logarithmic, and quadratic, which we've already touched on a little bit. Right? Exponential, logarithmic, and quadratic functions. OK. The first one we're going to talk about is exponential functions. OK? An exponential function, this one, exponential function with base b, that's why we call it b, the base b is defined by the following formula, or function. Y equals b raised to the x power. OK? Raised to the x power. OK? You can also write it, of course, as f of x equals b to the x. OK? These functions come up a lot when you're talking about exponential growth. Now, one kind of important exponential growth that you might be interested in is your money grows exponentially if you have it in a bank or in investments. Now, investments are a little different, like stocks and things, because then it goes up and down and whatever. But if you have it in a bank or a certificate of deposit, a CD or something like that, it will increase exponentially. Not necessarily as exponentially as you might want. For instance, let's say that you had $1. You put $1 in the bank. Okay? And every year, it doubles. Now, that's an impressive return. Right? Because after 1 year, how much would you have? You'd have $2 after 1 year. And let's say you're 25 years old now, and you want to retire at 65. Say you want to retire at 65. How many years of growth do you get? 40 years of growth? 40 years of growth. If you could double, would this be a good, would you take this if I could tell you you'd double your money every year for 40 years? Yeah, because after 3 years, you'd have how much? You're getting rich. Right? After 4 years? 8. So what we're doing is we're multiplying $1 times 2 to some x value, which is the number of years. Right? So what's the next one? $16, and you're at year 0, 1, 2, 3, 4. This is year, well, you do x. X equals 4, and your 2 to the 4th is 16. How many years did we say? 40 years. 2 to the 40th is approximately equal to $1 trillion. So if you could double your money every year for 40 years, you'd be a trillionaire. Now, to tell you how hard that is, there's never been a trillionaire in the history of the United States. You can't, it's really tough to double your money every year. But if you could, that's what it is. So exponential growth means growth fairly fast. Okay? Normally, you get much, much less, and we'll get into some of those details here in a minute. Okay? So let's look at the graph. Well, let's talk a little bit more about this. Okay? In this case, the base has to be greater than or equal to 0. Actually, it has to be greater than 0. It can't even be equal to 0. The base has to be greater than 0. And it also has to be not equal to 1. So you can have a base that's between 0 and 1, but you can't have a base that's 1, actually. Okay? And x has to be a real number. Okay? Let's look at the graph of this. Let's look at the graph of the same one we were just doing. We'll just use slightly different values. X and 2 to the x. And let's start out with -2. OK, this is where we got to remember what it means to take a negative exponent. So what we're going to do is we're going to go 2 to the -2. what does that mean if we were to write it in fraction forms? Anybody remember? 1 over 2 squared. 1 over 2 squared is what it means. Okay? So 1 over 2 squared is the same as 1 over 4. And we're just going to write 1/4 there. Okay? Let's go -1. That's going to be -1. 2 to the -1 is the same as 1 over 2 to the 1, which is just 1/2. So far, so good?
Why don't we do that? Why can't we just write it one way instead of confusing?
Why can't we write it one way?
Like instead of doing it to the name, why don't we just write it 1/2?
Well, because you want a formula. Remember, our formula is y equals 2 to the x. And then I plug in whatever x is. So x can be -1 or -2. And then you have to convert it to this. So it's a good idea. Why don't we just write it like this to start out with? But you can't write this one that way.
It's like everything's in code.
Well, yeah, I mean, it might seem like everything's in code. But really, it's just saying, how do you, in this case, it's saying, how do you take exponents? Well, remember, an exponent, 2 to the x, right? Or rather, 2 to the negative x, in this case, is 1 over 2 to the x. You just have to remember that formula. Whenever you see a -1, that's 1 over 2 to the whatever. Okay? I mean, I see what you mean, but I don't know what else to say. We have a formula, y equals 2 to the x, and whatever x is, we gotta know how to plug in to that correctly. What about 0? What's 2 to the 0? 1. Okay. Let's go up by 1. What's 2 to the 1? 2. 2 to the 2? 4, et cetera, et cetera. Let's graph this. 1, 2, 3, 4, -1, -2, -3, -4, 1, 2, 3, 4, and -1, -2, -3, -4. OK. So let's see. At x equals -2, y is 1/4. X equals -2, y is about right there. At x equals -1, y is actually all the way up to 1/2. At x equals 0, y equals 1. At x equals 1, y equals 2. And x equals 2, y equals 4. This is how this looks. If I was going to draw all these out, like that, except for the little squiggly there, where I messed up. Still can't draw very well. There we go. Now, does it ever touch the x-axis? Yeah. No. You find me a number, 2 to some number x, where that number actually gets to 0. Doesn't exist, right? You can say 2 to the -1,000,000, -1 million. And that's just 1 over 2 to the 1,000,000. Is that equal to 0? No, it's really, really small, but it never quite hits the x-axis over here. So this value is this is always positive. And remember how we were doubling our money, right? This goes up really fast on that side. And it goes down pretty fast on this side, too, but it never quite makes it to 0. OK? All right, so that's our first little exponential formula. Let's do an example we might have to use on this. This is 7.6 in the book. Yeah. Here's where we might use this. Okay? You guys know the population of the Earth is getting bigger and bigger every year, right? Well, it's modeled with an exponential function. Okay? So let's say that we have this function, g of x equals 2.566 times 1.017 raised to the x, where x is the number of years. X is the number of years since 1947. This is just a model, by the way. This is not saying in a year it will be exactly this population. It's just a model. People have looked at this model over time, and they've built this. what they've done is they've taken all the data that we've got up to 1947, and we said, well, if things continue the way they are, population will go up like this. Okay? Doesn't take into consideration things like modern birth control and that sort of thing. It probably doesn't. But we'll see how close it is. Okay? Let's see. Anybody know what the population of the world is right about now, 2013? About 7.5 what? 7.5 billion. Let's see how close this gets. Let's see how close this gets for us. Okay? 7.5 billion. So since 1947, that's the number of years. So how am I going to find out what x is going to be in this case? 2013 minus 1947. 13 minus 7 is 6. 9 minus 4 is 5. 56 years? 66 years? 76 years? Hold on. 76 years? 66 years. 13 minus 7 and then 10 minus, wait, yeah, it's 66 years. There we go. Were you right? I can do math on the board. OK, so we're just going to plug into this. G of x equals 2.566 times 1.017 raised to the 66th power. You got to be able to do this on your calculator. OK, so I want everybody to type in their calculator. If you have this one, I'll walk you through the buttons. If you have a slightly different one, you're going to have to do it a little bit different. OK, 2.566 times 1.01, hang on, did it wrong, 1.017. And then there's a little button on here. Actually, it's the little caret button, right? Caret, which means raised to the power of 66, equals g of x equals, hopefully everybody got 7.8 as an answer. If you didn't get that, you got to figure out how to do it on your calculator. Some of the calculators have y raised to the x or x raised to the y button. First you type the number, then you type the little that button, then you type the other number. Like it would be 1.017, then that number, then the other number. It's kind of the same thing as the caret. OK, 7.8 billion people. So that's not too bad. That's a pretty good estimate, actually. Right? Yeah. What will it be next year?
2065.
67. Try it. How about 7.9 billion? Yeah. So we're getting bigger by about 100 million people per year. That's a lot of people. A lot of people per year, if you ask me. A lot more mouths to feed in the world. But that's how you'd plug into there. OK, everybody get that? How to do that? OK. There's a special number which seems to happen a lot, or we seem to find a lot when we're dealing with exponential numbers. Okay? There's a number called e. Okay? The e actually stands for I think it's the exponential base, or the exponential function. And what this is this is a number, just like any other number, except that it happens to be like pi. It's irrational. Doesn't ever repeat. OK? It's well, I should write it like approximately equal to. E is approximately 2.71828 ... but it doesn't repeat. Like you can't figure out a pattern here. OK? And this happens to come up, like I said, a lot in these kind of problems, especially problems when you're talking about money growth and growth of other exponential functions. This is a big one. OK? Your calculator actually has a little button on it called e to the x. It's like e to the x, which we'll be using as well. Sometimes you have to hit the second function and then e to the x. OK? So we'll be using that function. OK? The exponential function. Exponential function. What's interesting about this calculus moment here, for those of you guys who eventually will take calculus, if you do, the exponential function, OK, actually, I think I'll graph it right here. the exponential function, if you were to plug in numbers for x and e to the x, right? Same thing we did before, -2, -1, 0, 1, and 2. You would get 0.135, because what's that? That's 1 over e raised to the 2. Okay, 0.135. You should try that and see if you can get it. If you did -1, it would be 0.368. If you did 0, of course, it's still 1. If you did 1, it's going to be 2.718, because that's what that number raised to the first power is. And if you did 2, it's going to be 7.389. If you're to graph this, we get same thing as before. Looks the same anyway. 1, 2, 3, 4. 1, 2, 3, 4. -1, -2, 1, 2, 0. Let's see. At -2, it's 0.1, so it's there. At -1, it is 0.3, so it's a little higher. At 0, it's 1, of course, as they all are. At 1, it's 2.7, about here. And then at 2, it's 7.8, so 5, 6, 7, 8, so about here. And then let's see if I can get this one. Like that. What's interesting about this function, just a little calculus for you. If you look at the slope at any point, the slope at any point is equal to that point. So right here, the slope, if the y value is 7.389, if you were to find the rise over run at that one little point, it would also be 7.389. Kind of a cool little trivia for you. Okay? But anyway, notice, also doesn't hit the x-axis and also increases, just like all the other functions. Okay? Exponential functions. Okay? We also have the inverse of exponential functions. Okay? The inverse of exponential functions are called logarithmic functions. Okay? So now we're off exponential, and now we're on to logarithmic functions. Okay? Logarithms are the exact opposite of the exponential functions. Okay? And let me show you what I mean. Okay? This is for x is greater than 0, and b is greater than 0, and b is not equal to 1. Same thing as before. Okay? We have this thing called a logarithm. We abbreviate it log. Y equals the log of base b, bear with me on this, x, okay, which is just equal to b raised to the y equals x. Okay? Notice it looks very, very similar to the other one, which we had y equals b to the x. This one is really x equals b to the y. Okay? It's the exact opposite. Okay? This is how we would write something like this. Log of base 2 of 16. How would I rewrite that? Y equals log of 2, log base 2 of 16. How would I rewrite that? 2 to the y equals 16. So in this case, what raised to the y, or 2 raised to what power equals 16? 2 to the 4 equals 16. Okay? Try this on your calculator. Oh, actually, you can't quite do it on your calculator because you don't have base 2 logarithms on here. You do have the log button, L-O-G. That log button means base 10. So let's try one like this. Log, whoops, y equals log of base 10 of 1,000. How would I rewrite that? Using that formula up there. How about, yeah, I get, well, all right, 10 to the y equals 1,000. What 10 to what power gives you 1,000? 10 squared is not 1,000. 10 squared is 100. So 10 cubed is 1,000. Okay, so 10 raised to the third power is 1,000. We just do that because we kind of can figure it out. But if you do this on your calculator, type the log button and then 1,000, tell me what you get.
303.
Nope, it's not 300. 3. Right? Because that's saying, that's doing this calculation for you and figuring out that that's what the value is. Okay? That's called the logarithmic function. Okay? Let's graph this function. Okay, we'll graph the log function. Okay? 1,000? Yeah. Okay. All right, let's do the same thing. We'll do base 2 again, because it's relatively easy to think about. Okay? If we have x and we have the log base 2 of x, okay? If we have 1/4, that's 2 to the y equals 1/4. 2 to what power equals 1/4? -2. Right? This is going to be the exact opposite of the graph we had before. If x is 1/2, -1. X is 0. 2 to what? 2 to the what equals 0. I'm sorry, I lied. Oh, is that? Sorry, I don't want to do 0. You can't do that. Try this. Try 2 to the what equals 1. There is no 2 to the what equals 0. 2 to the what equals 1. 0. That's 0. OK. And then we'll do 1. Oh, did 1. How about 2? 2 to the what equals 2? 1. 2 to the what equals 4? 2. Let's graph this. So if you look at the graph of this, 1, 2, 3, -1, -2, -3, 1, 2, 3, 1, 2, 3, -1, -2, -3, like that. Okay? If we look at x is 1/4, y is -2. That's about here. X is 1/2. X is 1/2. Then y is -1, about there. X is 1. Y equals 0. X equals 2. Y equals 1. And x equals 4. Y equals 2. Looks like this. Does it ever hit the y-axis? Nope. Does it go up really fast? No, it goes up really, really slow, actually. Logarithmic functions go up pretty darn slowly. Okay, it'll take forever to get up to 10, right, with a logarithmic function. Okay, and it'll go down really fast down here, the other way. Okay, logarithms. So remember that formula. Remember that formula that y equals log base b of x is the same as saying b to the y equals x. Okay? All right. OK. So let's try one with logarithms. I hope your calculators have an LN button. Do they have an LN button? Where is? Oh, it's actually the white. It's next to the E to the X button. The base for E, which is what we talked about, gives you the natural logarithm, which is ln. Okay? So if you have y equals log base E of x, that's the exact same thing as saying y equals ln of x, the natural logarithm of x. You just don't worry about the E in there. And you got a button on your calculator that does it. So there's a function f of x equals -11.6 plus 13.4 times the natural logarithm of x. Okay? This models the temperature increase in a closed car after x minutes. x minutes in a closed car. I'm not sure what the other conditions are, whether it's like a hot day or what. But let's say your car is closed, the air conditioner's not on, it's just like heating up in there, let's say. Okay? Find the temperature after 1 minute. After 1 minute, the temperature equals what? Or f of x equals what? Okay? If you do 1 minute in here, let's see what happens. F of x, this is another one, you just plug it in. Negative 11.6 plus 13.4 times the natural log of 1. Okay? Natural log of 1 says e raised to the y equals 1. What raised to anything equals 1? 0, right? Type this into your calculator. Natural logarithm and then 1. Or if you, Oliver, is your calculator the other way around with natural logarithm? You probably have to type 1 and then ln. What if you type ln of 1? What do you get? 0. So this is going to be 0. You're going to get negative 11.6 degrees. That doesn't make any sense. So this doesn't model this very well for 1 minute. But let's try 30 minutes. Sometimes these models aren't perfect. Let's try 30 minutes. Instead of natural log of 1, we're going to do natural log of 30 after 30 minutes. Negative 11.6 plus 13.4 times the logarithm of the natural logarithm of 30. Natural logarithm of 30 is 3.4. Yep, 3.4 in there. Is that just the natural logarithm of 30? Yeah, you did the whole thing out? OK. Times 13.4 gives you negative 11.6 plus 45.6. And let's see, 11.6. How about 33.9 or 34 degrees? About equal to 34 degrees after 30 minutes. I assume this is in Celsius or something, but I don't really know what the thing is. But you see how to do it? Everybody should be able to type this into your calculator and get 34 out of there. If you can't, practice it or figure it out. Stop by. What about? What's that? The natural log of 1 is always the natural log. Sorry, the natural log of 1 is always 0. The log of any number, the log of 1 of any base is 0. Okay. Okay, so those are exponential functions and logarithmic functions. The next one we have to deal with is quadratic functions. Now, luckily, we've already seen these. Okay, we've already seen quadratic functions, but we'll do them again, or we'll talk about them in a little more detail. Okay, quadratic function is a function that can be expressed like this. F of x equals, you've all seen this before, ax squared plus bx plus c. Okay? And remember, a, b, and c need to be real numbers. Real numbers. And a can't be 0. A cannot be equal to 0. Otherwise, it wouldn't be a parabola or a quadratic function. These are parabolas, by the way. Okay? If a is greater than 0, it opens upwards. If it's a parabola, if a is greater than 0. Okay? What do you think it looks like if a is less than 0? It goes downwards like that. Okay, and you can put the arrows on there if you want to go forever, because it goes on forever. Okay? So if I ask you on a homework or on a test or something, and you see it in this form, and it looks like this, 5x squared plus 3x plus 2, y equals that. This is a parabola. Does it face upwards or downwards? Faces upwards. Check. You just got 2 points. Okay? Make sure you remember to solve this just like you had to do for the test with the make it equal in the right form. So the y is over here and everything else is over there. Okay? All right, that's pretty easy. Okay? A parabola is symmetric about its axis. What does that mean? You can draw a line down the middle of the parabola. If the parabola looks like this side is exactly like this side. I didn't draw it perfectly, but they're identical on both sides. Okay? This point is called the vertex. Okay? And we can figure out the vertex very easily. To figure out the vertex, that's at a point where x equals negative b over 2 times a. This should look somewhat familiar. That's the first part of the quadratic equation if you took out the whole the radical part. Okay? At that value of x, that's where this little guy is. That's where the vertex is. Okay? If it happened to be there, the vertex would be at that value of x. If you know that value of x and you want to find the value of y, you got to plug that number back into your equation, and then you'll get a number for y. And then you'll have 2 points, or an x-coordinate and a y-coordinate, and you'll be able to plot it on the graph. Okay? We'll do an example of that. Do a couple examples like this. Okay? Any questions on that? Negative b over 2a. You have to memorize that too, but it's part of the quadratic equation, so you've already got it memorized. Okay? Let's do an example. Let's say we have f of x, or y, equals x squared minus 3x minus 4. Is it in the right form already? Y equals x squared minus, I can just write, I can replace this with y if I want. Yes. Yep, it is. OK, good. OK, does it open up or down? Opens up. Why down? It's this one, a. A has got to be, remember, this is a, 1. A equals 1. B equals negative 3. And C equals negative 4. So far, so good? Okay. All right, so it opens up. Opens up. OK, we know it's going to look like a smiley face. OK. All right, we want to find the vertex. OK. If we want to find the vertex, we can say x equals negative b over 2a. Well, we know what these are now. Negative negative 3 divided by 2 times 1 gives you 3 halves. That's the x-coordinate for the vertex. To find the y-coordinate for the vertex, we have to plug 3 halves back into this guy up here. So we say y equals 3 halves squared minus 3 times 3 halves minus 4. And then you just have to crank through this. 9 fourths minus 9 halves minus 4. Okay, we can do this by finding a common denominator of 4. 9 fourths minus 18 fourths minus 16 fourths equals what? 9 minus 18 minus 16. 9 minus 18 is negative 9, right? Minus 16? 25. Negative 25 fourths. There's the y-coordinate. So the vertex, if you were to look at the graph, right, you know the vertex is at 3 halves across, 1, 2, that's 1.5 across, and negative 25 fourths, which 4 goes into 25 6 times. So it's a little over 6. So negative. 1, 2, 3, 4, 5, 6. Like that. So that's the bottom of it. And it's going to go whoop like this. Okay? If I want to find where it hits the axis, well, that's the same thing we could do that you did on the test by making x equal to 0. At x equals 0. Okay? at, well, this will give you the y-intercept, where it hits the y-intercept. At x equals 0, let's do this. Y equals 0 squared minus 3 times 0 minus 4. Negative 4 is the answer. That 0 becomes 0, that's 0, and that's negative 4. So at point 0, comma, negative 4, 0, 1, 2, 3, 4 is where it hits the axis. So I've got 2 points now. Can I just draw it right now with those 2 points? It's not a straight line anymore. Can't do it with those 2 points yet. Not quite. We'll get there. Or we almost can. Now we got to figure out at when y equals 0. 0 equals x squared minus 3x minus 4. X squared minus 3x minus 4. I'll just do it like this. Does that look familiar? What can we do to that? We can break it down. What do we call that? What is it? Factor it. We can factor that, right? X and x, what's it going to be? Negative 3 and negative 4. 4 and 1, which is going to be negative, which is going to be positive? X minus 4, x plus 1. OK. So if we do that, if we set each one equal to 0, we get x equals negative 1 and x equals 4. And that's where y equals 0. When y equals 0. So now we have negative 1, 0, negative 1, 0, and we have 4, 0. 1, 2, 3, 4, 0. Now look at all the points I've got. What you can do now is you can now go, well, I don't want to be able to do it, but you can go whoop, like that, and that's what your parabola looks like. That's a lot of steps to do a parabola, right? But really, it's not. I mean, it's all the stuff we've been building up to until now. We know how to factor. We know how to set things equal to 0 and solve for the other ones. We know how to plug into the formula. It's kind of like quadratic equation. OK? And you can figure all those things out just by doing that. And that's what your parabola looks like. Not a very good parabola, the way I drew it, but that's what you can do. Once you have those points, you can draw it. Really, you don't really need this one if you don't want. You can just get this one and this one and this one and know that it's symmetric about that. But I might ask you all those points. OK? And that's there. OK, boy, that was a lot of stuff in like 45 minutes. Not even 40 minutes. Questions on this stuff? Want to do another one? We better do another one. See if I can find a good one. I tell you, what we also have to do tonight, by the way, is that we're done with that's finishing chapter 7. What we also have to do is start some like business stuff. Let's do one more of these. I'll give you one more. Here we go. X squared minus 2x minus 48. X squared minus 2x minus 48. X squared minus 2x minus 48. Y equals, or f of x equals. Here's what I want you to find.
This is going to be just the quadratic.
Sorry, this is going to be a quadratic function. How do you know? Because it's got the x squared in there. Yep. OK. All right. Question 1. Which way does it face? Up. So we know it's going to look like that. OK. Question 2. Where's the vertex? How are we going to find that? Well, we're going to need to know A, B, and C.
X equals
Negative B over 2A. Thank you. Good. OK. So it's going to be negative negative 2 divided by 2 times 1. Looks familiar. 1 is our vertex. OK. For the x value of the vertex. Right? How do we find the y value of the vertex? Don't need to set y to 0. We're going to set x equal to this and plug into this equation. So that's our x value. So in this case, our vertex y value is going to be 1 squared minus 2 times 1 minus 48. 1 minus 2 minus 48 gives you negative 49. OK, so we know it faces up. Now we know the vertex equals 1 comma negative 49. It's going to be way down there on the graph. If we want to find the x-intercepts, this is where it hits the x-axis. What does that mean y is? Somewhere around here. What is y in that case? 0. Nope, we already did the vertex. Now we're just finding where it hits the y-axis, because it's going to look something like this. Where it hits there and where it hits there is what we're trying to find out. Doesn't y equal 0 at that point and that point? Sure. We could do the, right, we're going to do the, well, we're going to do the, not the FOIL method, we're going to do the factoring. So let's factor this. X squared minus 2x minus 48. Factor it. X and x. 6 and 8. I like it. Which is which? Minus 8 plus 6. So that means x equals negative 6 and x equals positive 8, because we're going to set each one equal to 0. OK, so now we have 2 points for the x-intercepts. We've got negative 6, 0, and we've got 8, 0. OK? And if we want the y-intercept, which is where x equals 0, that's easy. If x is 0, that means 0 minus 48. 0 comma 48 is where it hits the y-intercept, or the y-axis.
Can you please repeat the starting number?
Yeah. So if I want to know where it hits the y-axis, that means x equals 0. Because if you look at the graph, wherever it hits the y-axis, what's the x-coordinate equal to? Right here, what's x equal to? What's x equal to here? Nope, 0, because it's this way is x, right? What's x equal to here? 0. X equal anywhere on this line is 0. Right? So what that means is you'd plug in 0 up there. 0 squared minus 2 times 0 minus 48. Y equals what? Negative 48. OK? And then you'd want to look at a graph. I would give you a little graph to look at. And you'd say, OK, look, all these points, you've got to line it up and figure out which points are where. It's going to look something like this. We know the vertex is 1, negative 49, which is way down here somewhere. And we know that it crosses at negative 6, 0. And it crosses at 8, 0. I'm just kind of guessing the values here, or doing it quickly. And then the y-intercept is at negative 48. So that's like right here. So this is what it's going to look like. Like that. OK? Not too bad, I hope. All right. All right. Go away for 15 minutes. Then we'll come back and keep going. Let's get going on the beginning of chapter 8, which is all about percents and sales tax. And it also talks about income tax. But we are not going to do that. Here's why. Because A, it's not really mathematics. I mean, it's using arithmetic and whatever, but it's completely American-centric and has to do with a bunch of stuff that really, if you're still doing your taxes on paper, you're crazy. You should be going to turbotax.com or one of the other taxthings.com or whatever, doing your taxes there. So we're not going to talk about income tax. I don't really care that you need to know those details. You might have had to like 20 years ago, but now you can just let a computer do your taxes for you, and you plug in the right numbers. Way easier. OK, but we are going to talk about percents and sales taxes, because those are still important, especially now that companies like Amazon and so forth force you to, or they're going to start charging sales tax. And they already have for some states. OK, percent and sales tax. Not too bad. We've already done some of this stuff already. This is section 8.1. Percent means per 100. That's all percent means, per 100. Okay? We express numbers as part of 100, per 100. Okay? So if we have 1/4, right? That is equal to 1 times 25, and we want to make this one 100. 4 times 25 gives you 25 100ths, or 25 and the percent symbol. Okay, 1/4 is 25%, because it's what you would do in your calculator is you go 0.25 and then multiply that by 100, and that would give you 25%. Okay, that's all there is to percents. Okay, to express a fraction as a percent, divide it, multiply by 100, add a percent sign. We're done. Okay, here's an example. 3/8. Okay, what's 3/8 on your calculator? 0.375. Okay, that becomes 3.375 times 100, 37.5%. Okay, this is not rocket science. Okay, this is percent. Well, this will be on your next test. There'll also be like graph the following parabola. So. Okay. How about this? 0.43 in percent is what? 43%. So easy. Okay. All right. How about 27 in percent? 2,700%. All right. If you see something that's 27% interest, 27% interest, what is that in decimal form? 0.27. You go backwards by dividing by 100. Okay? It's the exact opposite. To go backwards from a percent to a decimal, you divide by 100. Okay? What's the most normal thing we see as percentages? Taxes. Why? Because Uncle Sam's going to get his money. Right? And how does he do it? He charges you a certain percent of the value. Okay? Okay, so sales tax, which is the only one we're going to talk about, remember. Sales tax, okay, is the tax rate times the price. Okay, and the tax rate a lot of times is in percents. So here's an example. Sales tax rate, 9.75%. I don't know any states that make you do a sales tax of that much, but that would be a lot. Okay? Let's say you get something that's $375. $375. Okay? Sorry, we'll do it $372. $372. Okay? How much tax is there if it's a 9.75%? Okay, well, how much tax is owed? Well, you say, divide that by 100, first of all. 9.75 divided by 100 equals 0.0975. Okay? A lot of people will actually screw up and make it 0.975. But that would be 97%. Right? It's 0.0975. Okay? 0.0975. Okay? Convert that to, so it's now converted decimal. And then we multiply that, 0.0975 times the price, 372. And we end up getting $36.27 for the tax. So the total cost of the whatever you're buying here, total cost is just going to be 372.00 plus 36.27, which gives you $408.27. Okay? Started out 372, ended up at 408.27. Okay? All right. We can also talk about percent and change. No, not change like the money change, like that horrible test question I asked you, right? We can talk about percent and change in terms of the percent increase or the percent decrease of something. Okay? You guys still writing this one down? No? OK. Let's do this. All right. The percent increase, something percent increase equals the amount of increase divided by the original amount. Not so hard. The original amount. The percent decrease is the exact opposite. Amount of decrease divided by the original amount. Okay? But you have to remember to express this as a percent. Express as a percent. In other words, as the little percent sign, with the little percent sign. OK. Here's your example. A battalion begins a mission with 570 soldiers. So you start out 570 soldiers. OK? Start with. At the start, you have 570 soldiers. In 2 months, 2 months later, okay, people get hurt, you have medevacs, people get in trouble, if you're from Kentucky. And you didn't hear me say that. And then, let's see what else happens. People get taken up by higher headquarters, et cetera, et cetera. Okay? You end up with 530 soldiers. Okay? Do we have a percent increase or decrease? Percent decrease. Okay, we know that right off the bat. Okay, and how much is it? Well, we look at the amount of the decrease. In this case, it's 570 minus 530, because that's the amount of the decrease, divided by the original amount, 570, gives you, how about 40 divided by 570? And if you divide that out, you get 0.070, which is what percent? Yeah, times 100, and you get 7% decrease. Okay? That wasn't too bad. Always round to the nearest percent. I mean, if you want, you can do a 0.5% or whatever, but point something. But generally, the easiest is to just go to the nearest percent. Okay? All right, here's another example. Sales tax example. Or a sale, not sales tax, a sale price example. Let's say you go and you buy a jacket at the store. Not that any of us need to buy jackets right now. But you buy a jacket. Okay? The jacket regularly sells for $98. Funny story. A friend of mine used to work in a golf pro shop, of all places. Right? You know, you buy like the jackets and whatever. And a friend of his came in and said, do you ever sell these jackets that are like, you know, $180 or something for this stupid little windbreaker? And his friend said, the guy that I know said, well, we always mark them way up. And then he said, but I bet you I can sell that jacket today if I, you know, they mark it up like over like 50% or over 100%, right? Because people will buy it. People play golf and it's expensive and whatever. They buy the stuff. He said, watch this. He took the price tag. He went from like $180 down to $90. And he wrote, no, I think he went only down to like He went from like $180 to like $150. He crossed off, said $150, and said something like 50% off. He wrote that on there. Somebody just swiped it up immediately because they're like, wow, 50% off, even though it wasn't anywhere near 50% off. Actually, I think he probably could have put just 50% off and would have sold fine. It's all psychological, right? OK, so the jacket cost $98. The sale price is $83.30. What's the percent decrease? Okay, percent decrease? 98 minus 83.30 divided by the original price, which was 98. Okay? If you do that out, this is 14.7 divided by 98. 14.7 divided by 98 is 0.15, which is 15% off. Yeah. What's that?
When you say 0 point, whatever the number is, I'm thinking like 0.0.
Oh, yeah, when you say 0 point, I always try to put it like that because that tells you exactly where the decimal point is. Sometimes you miss the decimal point if you don't. You might not notice it's there. So I always try to say 0.15, but you're right. You got to remember it's not 0.015. Yeah, good. OK. So let's say a manufacturer of some sort of widget, whatever a widget is. He can make them for $170 each. They're expensive. But then he can sell them, sells for $220 a piece. What is the markup? In other words, what percent does he mark it up? Or what percent increase is there? 220 minus 170 divided by the original price, 170, equals, in this case, that is 220 minus 170, 0, 12 minus 7, 5, $50? Or $150? $50. Is it? Yeah, $50. Divided by 170 gives you 0.29411. We're going to just make it 29%. 29% increase. Okay. All right. Next question. A store is holding a 10% off sale. Woohoo. These days, that doesn't sound like much. 10% off sale. 10% off. Okay. You have a coupon for 10% off. Okay. You also have a coupon for 10% off. Okay. So you have a coupon. There's a 10% off sale. And you have a coupon for 10% off that. Okay. How much do you pay for a $120 pair of shoes? $120 shoes. You pay how much? How many people think you can just take 20% off? I don't think it works that way.
Take 10% off of it.
Yeah. Take 10% off, then take. Let's see what happens when we do this, OK? So 10% of 120 the first time is 120 times 0.1, right? Which gives you, well, yeah, 20%. That gives you the amount off. So that gives you what? $12 off? OK, $12 off. So that means the price is now $108 because it's 120 minus 12 equals 108. Okay, now it's 108. Okay, now take 10% of that because you got the 10% off coupon. 108 times 0.1 equals, what is that? $10.80 off. So then 108 minus 10.8 gives you 97.2 0.2, or $97.20, and that's what you pay. Okay? If it was 20% off, what would you have paid? $120 times 0.2, which is 24. And 120 minus 24 is $96. So you can't add the percentages quite like that. Okay? It'd be nice if you could do that, but it doesn't quite work that way. Okay? I mean, think of it this way. Let's say you had a 50% off sale and you had a 50% off coupon.
Free.
It's not free though, right? You'd think that'd be free because you'd be like, oh, it's 100%. But no, it's 50% off first and then 50% of that. And that's not free. That's why it doesn't add up together like that. Be kind of cool. 75% off sale and you have a 75% off coupon. You get money back, right? It doesn't work that way. Be nice if it did, but it doesn't work that way. Okay? All right. Questions on that? That's it for that section. That wasn't too bad. Okay? So why don't you do this? Work on 5. If you have already done it, great. 5 through 12. I do have, I'm not going to give these out to you tonight. We've done too much tonight. But next week I'll hand out some more word problems that the guy who runs the course for the whole school said, make them practice these problems because they'll see one on the final. All right, so I'll give these off next week. Work on 5 through 12. If you're happy with those, then you can go. And if you want to work on the test now to finish that up, you can do that as well. OK? Good job.